Okay, imagine you type one simple search into your app, find the user with this email address, and you wait 1 second, 2 seconds, 4 seconds for one single row. That's not a bug. That's your database doing exactly what you told it to do, the slowest possible way. Let me show you why, and then let me show you the one line of code that fixes it. Here's what's actually happening. You've got a table of users, 10 million of them. Each row has an ID, a name, an email, a city. And when you ask the database to find one specific email, the database has no idea where that email lives. So it does the only thing it can. It starts at row 1. Is this the email? No. Row 2. Is this it? No. Row 3. Row 4. Row 5. On and on, all the way down, until it either finds a match or runs out of rows. Engineers call this a full table scan, and it's exactly as painful as it sounds. Now, here's the thing. Think about a really thick textbook. Say you want to find one topic in it. You could start at page 1 and read every single page until you spot it. That works. It's also insane. So what do you actually do? You flip to the back, to the index, and the index is just a sorted list. Topic on the left, page number on the right. You find your topic in seconds, you jump straight to that page. Done. A database index is exactly that. It's a sorted copy of one column that points back to the full row. That's the whole idea. So let's build one. We take that email column, we pull it out of the table, and we sort it alphabetically. Alice, Bob, Carol, David, Aaron, Frank, Zara. Then the database stacks those sorted keys into a tree structure called a B tree, a balanced tree. Picture it like this. At the very top, there's one node. Below it, 2 branches. Below those, more branches. And at the bottom, the actual keys, each one holding a pointer to where its row lives on disk. Every path from the top to the bottom is the exact same length. That's the balance part, and that's what makes it fast and predictable. Now, watch the search happen again, but with the index. We're looking for Carol. Start at the top of the tree. The root says David. Is Carol before David alphabetically? Yes. So go left. Instantly, we just threw away half the data. We didn't check it. We didn't read it. We eliminated it with one comparison. Now we're in the branch that holds A through C. Follow it down, and there's Carol. The key gives us a pointer. We follow that pointer, and we pull the row. 3 reads, not 10 million. 3. And this is the part that should really land. Without the index, the work grows in a straight line. Double your table, double your search time, 10 times the rows, 10 times the weight, forever. Engineers write that as O of n. With the index, the work grows logarithmically. O of log n. Every single hop down the tree throws away half of what's left. So going from 1 million rows to 10 million rows, that barely adds a couple of steps. 10 million rows becomes roughly 24 reads instead of 10 million. That is about 400,000 times less work for the same query on the same data. So indexes are magic, right? Add them everywhere? No. And this is where beginners get burned, so stay with me. An index is a second copy of your data, sorted and stored on disk. So first, it costs storage. That copy is real and it takes real space. Second, and this is the big one, it slows down your writes. Every time you insert a new row or update it or delete it, the database doesn't just change the table. It has to go update the tree as well and keep it balanced. So if you put 10 indexes on one table, every single write now does 11 jobs instead of 1. And third, an index nobody uses is pure cost with zero payoff. It eats space, it slows your writes, and it gives you nothing back. So here's how you actually use this in real life. Index the columns you search on, the ones in your filter conditions, index your foreign keys, the columns you join tables on, and index them on both sides. Index the columns you sort by. And that's mostly it. Don't index everything. Don't guess. Ask the database instead. Every major database has a command that shows you exactly how it planned to run your query and whether it used your index or fell back to scanning the whole table. That's not an advanced trick. That's a normal way to check your work. So here's the one thing to walk away with. An index trades storage and write speed for read speed. That's the deal. That's all it is. Most applications read far more than they write, which is exactly why that trade is usually a bargain. Index the columns you actually search, measure the result, and don't add anything you can't justify. If that made sense, hit subscribe. We go this deep on system internals every week. See you in the next one.